Yeah, so welcome everyone to this 19th e-YEG webinar. Everyone can hear me right? If there is any problem, just let us know in the chat somewhere. I can probably still see the chat. Yes. So this webinar we try to organize every month or every 2 months together with the Young Engineering Geologist group from the International Association of Engineering, Geology and the Environment. And today's webinar, we're talking about the direct and coupled effect on residual shear strength, as you can see on the screen of Núria, Pinyol. And we would specifically align this topic into like what it means to, for example, landslide. So it's addresses a fascinating and emerging topic at the intersection of engineering, geology, geomechanics, and climate-driven hazard processes. We are honored, and together, all of us, let's welcome our first speaker, who is Dr. Núria Pinyol. She is internationally recognized for her geotechnical and engineering geology works related to landslide mechanics, soil stability, constitutive modeling, and advanced numerical analysis of large deformation problems. Research has significantly advanced our understanding on the residual shear strength, strain rate effect, thermomechanical coupling, and landslide responses, including the reservoir-induced and climate-related processes. So a recent work exploring the temperature effect on the residual shear strength and the implication of landslide behavior has opened up important and new perspective of hazard assessment in a changing climate sort of scenario. Let's put our hands together to welcome Professor Pinyol on the first run, and then I would introduce the second speaker, Dr. Gianvito Scaringi, afterwards.
Okay.
Núria, the floor is yours.
Thank you very much for your introduction. I share my screen.
I could see it, yes, before, but now, yeah, it's coming. Perfect.
Okay. Thank you very much. Thank you for your introduction, invitation. It's a pleasure for me to be here and to share this lecture with Professor Gianvito Scaringi. We are here to talk, as you say, the effect of temperature on the residual shear strength and the implication for landslides. I would like to show you the work that I carry out with my colleagues here in Barcelona in this topic. We started to explore the thermal pressurization in landslides in order to understand the catastrophic acceleration due to thermal interaction, and we started with developing the basic concepts and formulations, later on the numerical modeling, and finally we try to look for experimental evidences. And later we focus on this second part of my presentation, in which we try to analyze if we can isolate the direct effect of imposing changes in temperature on the residual strength, because at the end is this strength that controls the evolution and the acceleration or run out of the landslides. And this part we explore mainly from an experimental point of view. Then we moved into the first part to understand the thermal pressurization. This phenomena was invoked to explain the catastrophic acceleration of some landslides, in particular the acceleration of Bayonne landslides that you know for sure, that occurred in Italy in 1963. It is one of the most catastrophic landslide events of the 20th century, because 270 millions of cubic meters of rock were mobilized at speeds exceeding 25 meters per second, which is more than 100 kilometers per hour, then this mass impact to the reservoir and the wave overtopped the Bayonne Dam and destroyed the village located downstream in the main valley. The concepts of the phenomenon of thermal pressurization is also invoked to explain more recent landslides. An example is these landslides occurred in Taiwan, triggered by the Chichi earthquake in 1999. This is the Shiver-Zhanshan landslide, and this runout is explained, or it is justified for some authors because of the thermal interaction again, and others catastrophic landslides are think that maybe the cause of this large runout, in this case in San Juan de Grijalva landslides triggered by a drawdown in 2007 in Mexico, and probably also occur because the thermal interaction may have an important role. The fundamental concepts and the physical phenomenon behind the thermal pressurization is that the heat generated due to frictional work induces increments of pore water pressure, which in turn reduce the effective strength and then the available strength. These ideas have been developed by several authors since Habib 1967 and others, and the concepts and the formulations are not equal for all of the authors. Some hypothesis changes, but the idea is always the same, that the temperature induced due to this frictional work induce a loss of effective of the available strength. Then the governing equation of this phenomena that we implemented is described here. The idea is that this frictional work is defined, that dissipates in heat at shear bands during motion, is defined with these equations, that the frictional work is made equal to the heat according to the first law of thermodynamics, and this heat eventually may induce this heat induces an increment of temperature due to the energy balance equation, and then eventually this temperature may induce excess pore water pressures due to the constraints of expansion and flow. It is defined by means of the mass balance, the mass of water and solid balance. This temperature may induce this pore water pressure that in turn, depending on the constitutive equations considered, induce a loss of strength. In our case, the constitutive equation that in this first part of the analysis was modeled by means of a simple Moore Coulomb model, without including the temperature in the constitutive behavior of the material. But this effect of the pore water pressure may induce changes in the mechanical response of the soil, which, if you apply the momentum balance, the equilibrium, it induces the acceleration of the landslide. And then this process is self-feeding process because as the landslide accelerates because of the loss of the effective stress, this acceleration induces again additional heat, and this process is self-feeding because it accelerates it again with this new increment of pore water pressure. But it depends also, the evolution depends, as I said, on the constraints of the expansion and flow. all of these equations were implemented in a general numerical tool in order to solve boundary value problems, and we selected the material point method, which is suitable for simulating large displacement by combining Lagrangian and Eulerian discretization. The idea is that the materials are discretized into material points that carry all of the information and can move throughout the domain, which in turn is discretized with a computational maze that we use to solve the equations. The results are finally mapped to the material points that update their position without involving distortion of the computational maze. With this, we could include all the questions, but what we observe is that the direct implementation of the equations to the material point method leads to a pathological maze dependence because the rate of generated mechanical work per unit of volume depends on the shear band thickness. And as you know, the thickness of the shear bands when modeling with a continuum method such as standard MPM, but also standard finite element method, depends on the mesh size. And then what we observe is that the results of, for example, in this simple geometry, the results in terms, in this case, of run-out maximum displacement depends completely on the mesh element size. Then if we increase this element size, the displacement reduces significantly because the accumulated pore water pressure due to a given displacement was lower when the element size was larger. And as you can see here, the displacement, the velocity starts, the slope becomes unstable, but given a displacement, the pore water pressure accumulated is larger, even having the same properties of the material, because the only difference, the unit difference, is the element size. In order to overcome such limitations, we develop a numerical solution which consisted in defining numerical embedded joints. And the idea is calculating the work dissipated as into heat by means the deformation associated with a material point, but localize it into a shear band whose thickness is defined by the user, and it doesn't depend on the mesh discretization. Note that this procedure is not equivalent to non-local regularization that typically is applied in finite element method, because in this case the thickness of the embedded shear bands are smaller than the element size. And then once it defined, we define a local equilibrium to solve the dissipation of pore water pressure and temperature defined or generated in these numerical embedded joints. And once this local equilibrium was defined, the rest of the equilibrium with the rest of the mesh is applied as usual, or as the standard methods done. And with that, you can see that the incorporation of the embedded joints prevent the pathological mesh dependence of the heat generation, and we observe the similar, not obviously the effect of the mesh is there, but not in a pathological way, and the excess pore water pressure measured is almost the same, and also the final and the displacement and the final geometry calculated. Then with that, we wanted to evaluate what are the important parameters actually controlling the response of the thermal pressurization in accelerated landslides. And we observed that the most relevant parameter is the permeability, because if the slow material is relatively pervious, with a permeability equal to 10 to minus 5 meters per second, the results are similar than the one obtained without heating coupling, without the thermal interaction. On contrary, if the permeability is significantly lower than around 10 to minus 11, for instance, the effect is relevant, and then this permeability prevents the dissipation of the thermal induced pore water pressure, and then it leads to the acceleration and a larger displacement of the landslide. Here you can see how this low permeability prevents the dissipation of this excess pore water pressure, and it is not the case when the material is more pervious. And with that, we could model the landslide, the Bayonne landslide, for the first time without simplifying the geometry and using global or general numerical tool, which is useful because you can define a better or more realistic geometry, and also you can introduce the effect of the strength of the mobilized material during the motion. We also include the water, and we simulate not in the actual time, but we simulate in the reservoir impoundment and how the landslide moved. And here you can see the video of this motion and this acceleration, and here you can see the shear bands defined. We can observe that the results shows that the landslide is speeded at more than 20 meters per second and run more than 300 meters until reaching the opposite flank, which is more or less what is estimated according to the wave, the height of the waves generated. We also simulated the subsidence and landslides more recently. In this case, we applied the earthquake in the base of the model by prescribing the velocity, and we explore if we were able to simulate the final geometry of the landslide by considering first a simple Moore Coulomb perfectly elastoplastic model. And what we observe is that if we consider the description of the materials and the characterization according to the literature, we could define or we could reproduce the sliding. However, not the run out, because the displacement was calculated was underestimate significantly the final run out, which was more than 1 kilometer. This is the final geometry in blue of the landslide. Then we introduce we describe the materials with strain softening according to the results of the laboratory test carried out on the material involved in the sliding surface. And then the results, the effect is significant and the runout increases. However, it remains smaller than the observed one. And then we explore if the thermal effect could explain this large landslide. This is without thermal effects, only including the strain softening, as you can see that it is moving and the runout is larger, but it finally stopped. And when the thermal effects are included, it's observed that we can model the runout, and the final geometry is more or less similar than the observed one. This is an exercise to show that if the in the shearing bands is able to, the temperature is, you consider the increase of the temperature and you consider the accumulated excess pore water pressure, if the materials are impervious enough, you can explain the acceleration of some of some landslides as the shear engines and landslide. This is the video of the results in the NPM, including the thermal effects and the embedded shear bands. But at that point, we wonder, or we wanted to explore the observation, or we are interested on experimental evidences regarding the thermal pressurization due to shearing, because in the literature this data was very limited. And then some years ago in the laboratory at UPC, a rapid ring shear test was designed and built. And this test is able to is a ring shear test, but able to control and measure the temperature and pore water pressure, and the velocities applied can be in this range, 0.1 kilometers per hour to 20 kilometers per hour. Then the idea was to apply a vertical stress and control the vertical displacements, and measuring the pore water pressure and the temperature developed in the sample during shearing at very large velocities. Here I present some recent results very quickly. Samples of low plasticity clay taken from a landslide occurred in Catalonia, an incipient landslide located in a flank of a reservoir, and we're analyzing these landslides because we want to assess or evaluate the potential acceleration of these landslides. And then this material is the one tested in this rapid ring shear test. And we observe that during the test, when the displacements are accumulated at different velocities, the temperature increased significantly, and it involved an increment of pore water pressure inside of the sample, that obviously controls the effective strengths and the strength. And then at this point, we wondered if the temperature generated by the frictional work, or maybe imposed from outside, could affect the residual strength, and also if we need a very large increment of temperature, or only a few degrees could have an effect on this value, on the residual, this parameter, this residual strength that control the displacements and the evolution of landslides. As you know, it is widely evaluated in the literature what factors can affect the strength, such as normal stress, shear velocity, chemical features of the pore fluid, but the temperature was not explored at that time. And there were some theoretical developments, but we wanted to focus on the experimental results and evidence. But we are aware that it's difficult to ensure that the couplings effects are not present in the experiments that we carried out. But with this aim, in order to evaluate the effect of the temperature, the external temperature on the residual strength, we define a comprehensive program in which a wide range of materials, from fine sand to high plasticity clay, were tested at shearing at different temperatures. This material, for instance, in particular, the Castelldefels sand is a very fine sand, very pervious. The Barcelona silty clay is a material located here at UPC campus, extensively used in our laboratory in the research of unsaturated soils. And then we also tested 3 high plasticity clays of bentonite, also extensively analyzed, but in the field of nuclear waste storage. We add some additional samples, mixture samples, constituted by the Castelldefels sands and the Febex clay and the MX80 clay, which are these high plasticity clays. And then we modified the broomhead ring shear equipment, but the temperature, in order to control the temperature, and the temperature was controlled by cooling and heating the water surrounding the cell where the sample was located. The idea is that the water circulate from this deposit and the temperature were imposed and controlled, and then we ensure the temperature of the system and of the equipment, and we ensure that the temperature was in the sample evaluated. The results, the test, the protocol of the test is shown here. We perform heating and cooling tests. Some tests were started at the laboratory temperature, and some tests were previously cooled or heated, and then we apply the change of temperature during shearing, and we ensure that the transient effects were not evaluated, in the sense that we changes the temperature and the shearing remains and was applied, and later on we evaluate the strength in order to evaluate not the transient effect of the change in temperature, but the strength at this new temperature. In total, we performed 70 tests of the different samples described. And here I show you some results. This is the temperature applied in green, and the results are shown in red. And in case of the Castelldefels sand, this fine sand, we didn't observe any reaction, any effect. But and in the low plasticity Barcelona silty clay, the effect was not evident. But this effect increased with the plasticity, with the content of clay and with the plasticity of the clay. You can see this effect in the Canellas clay. This is the material of the landslide that I showed you previously. And you can see when the material, when the sample, the temperature decrease, the strength increase. And this effect is symmetric in the sense that when the temperature increase in the same magnitude, the strength decrease also in the same magnitude. It was also observed in the boom clay and in the Febex clay. Here you can see the results in terms of variation of the temperature and increase or decrease of the strength in terms of the increments of friction angle. And you can see that sometimes the results are not very clear, but the tendency, we observe that the effect is clearly increasing with the clay and with the plasticity. Here in this test, the effect is not so large, but we have some problems with these samples because they during the shearing they exhibit some expansion. Then we cannot interpret the results in the same way. And here I plotted this effect of the temperature, the variation of the temperature on the friction angle with the plasticity index. But it is just a representation because there are other reasons which explain this variation, this effect on the strengths because of the temperature. And then I move into the conclusions. A numerical tool has been developed to model thermal pressurization inducing acceleration on landslides, and the permeability is the most relevant parameter controlling the coupling thermal effects. And we observed in a rapid shear ring experiment that there are physical evidences of this excess pore water pressure generated during friction, and at least at large velocities. And in parallel, a consistent experimental program to evaluate the effect of imposing temperature from externally, not due to the frictional heating on the residual strength, has been presented. And what we observe is that increasing temperature leads to a decrease in residual friction, and this effect is progressively more pronounced when soil plasticity increases. And then temperature effect, intrinsic, direct, or due to the interaction and the water pressurization, go in the same direction, namely increasing the risk of landslide acceleration. And okay, this is the final part of my presentation. I would like to thanks for your attention, and also to thanks my colleagues that collaborate in this work that I presented. Thank you very much.
Thank you, Núria, for that excellent presentation. Was very clear to me, because I relate more to this topic than anyone else in this room better, I think. Is there any questions from the audience? If not, I can start with a few, actually, if I may. You started with the material point formulation. I tried a few times during my master thesis to use this framework. So, like, briefly, could you just simplify to the rest of the group, like, what is the rule of thumb on using, like, how many points would you need in a grade? Or is there like a rule of thumb to use it? Like, how do you start, essentially?
This is like finite element method. You know that when you have a small sample, you use a small elements, and when you have a large model, these elements are very large. And at the end, the questions are solved in the notes. Then it's better to have a very small mesh in order to have better results. Okay, but obviously it has a computational cost. But once the element size is defined, as in the same criteria more or less than you do with finite element method, other continuum methods that you use in numerically, then the number of material points helps you to prevent some numerical issues that NPM has. Then if you use more numerical material points, it's better in the sense than problems of cross-selling and other kinds of problems with the integration of the stresses, and these kind of things are useful to have more numerical particles. But it is important to have in mind that the questions are solved in the mesh.
Yes.
And then the criteria is the same than a continuum method like a standard finite element method.
Mm-hmm. And just to follow up, also regarding the stability of the model, because multiple times as I use like smaller time steps to solve the equations, I see that the material points are like flying. I don't know if it's just a formulation of mine that I have this problem, but if I use like a really slightly larger time step, then there is a bit of stability problem. So is there also like a rule of thumb that you need to have really small time steps for fast movements or something like this? Or if you are like modeling a very, very fast movement, then you probably need to have a very, very, very small time step, right?
Yeah, okay. It depends on the type of time integration that you are using. I suppose that if you are using an explicit integration, then finally you have to use a very small time steps. But it is related with the integration of the time integration of your code and how you deal with that and the phenomena that you are simulating. In the sense that obviously if it is elastic, there is no problem, but when the non-linear processes are there, it is more difficult. And then there are other issues related with the integration of the questions that reach some problems of instability, even having a very small time step when you are integrating in explicit. Then in NPM you have the same problems that you have in finite element method, and additionally you have the problems of using a Lagrangian mesh, using material points. Then you have to combine both type of problems to solve in a good manner, but this is in the I want to say that these problems of integrations of discretizations are the same that finite element method.
You see. Mm-hmm. Yeah, it's clear. Thank you. Just moving on to the later part of the presentation, since, as we mentioned before, since we do like similar kind of tests, I just wanted to understand your opinion in like reading the shear measurements on the ring shear box, like the slow shear and the slow shearing device that you showed, and then the circulation of the heated liquid in the cell. And like, do you think there is any issue of like the cell getting expanded and that hampering the shearing measurements? Did you look?
Yes, I think that we have to what we are trying to do is that the effect of the temperature have to be evaluated. If we want to evaluate the intrinsic effect of the temperature on the shearing, it's important to remove the water, because we are not sure if we are able to isolate this effect, the effect of the dilation of the water. Even having the sample very small, and even if you do some calculations. You assume that if some excess pore water pressure is generated due to this change of temperature, or even if there is a decrease of this effective stress due to the cooling, it is dissipated during the time of the test because of the dimension of the sample. But we are not sure of that. We are not sure because we cannot measure at that, and then we may are measuring the coupling effects also in these tests. Then I think that we have to explore the intrinsic effect of temperature without in completely dry samples. In fact, the effect of the strain rate on clays was analyzed. We analyzed this effect, the effect of the strain rate in unsaturated soils, in dry soils. It's true that you have the effect of suction, but you can control better the change, the effect of the velocity of the temperature, even having this suction. But because as you said, it's difficult to isolate the effect, the intrinsic effect.
I see. Before I move on to the question in the chat, I have one final question, and that is relating to the shear rate and like your impression on like using the differences in the result of using like different shear rates, because our shear rates are like extremely slow, and on test that you show it's like 0.4 millimeter a minute, if I'm not mistaken, right? The shear rate.
I don't understand you. Sorry, because I was reading the chat. Can you repeat, please?
No. The rate of shear you use on the ring shear device, the slower ring shear device that you showed, was 0.4 millimeter a minute. And I was just on your impression, like the shear rate of using faster or slower rates onto the effect of temperature. Like, what do you think? Is there like a variation due to it or something?
Are you talking about the rapid shearing test or the broomhead?
The bromide, the slower, yes, bromide test, yes.
Yeah, we had problems when we changed the velocity in this test because the material go out when the velocity increases. But the test I presented at the velocity indicated, the 0.4 millimeters per minute, we could control the volume of the samples, and after when we see the sample after the test, it was confined, and we observed that the results were consistent, and we didn't have problems. But I had problems when increased this velocity, and then it's for the reason that when we evaluate the effect of the velocity in the broomhead test, we use dry materials, because with water it was not possible for us to control the material was removed during the test. And if we put some materials to confine, then it affects the resistance of the equipment, and then we didn't apply the velocity that we wanted, and then we don't measure the strength of the soil. We measure the strength of the equipment, and we had difficulties in this aspect. Yes.
Yeah, thank you very much for the very clear answers. I would move on to the question in the chat. I have a question from Mattea. He says, to what extent might uncertainty about the in-situ permeability measure affect the reliability of your model's acceleration predictions?
Okay. We did a lot of sensitivity analysis on the permeability, for sure, because we observed that In fact, I have some graphs in which the acceleration of a given landslide was in the velocity, the final velocity, the acceleration increased with when the permeability was low. Otherwise, when the permeability was larger than 10 to minus 6, 10 to minus 5, 10 to minus 4, the effect of the temperature was insignificant, it's negligible. And then we need to have a material in the shear band with permeabilities lower than 10 to minus 10 in general. Because otherwise the temperature, or the slide start to move, the temperature may increase, it induces a larger it induces an increase in pore water pressure, but it dissipates during this motion, and then the strength is recovered. You need to have a very low permeability, otherwise it doesn't accelerate. And in fact, in the case of sugar and landslide, we also apply a range of permeability in order to ensure that for the permeabilities estimated for the materials of the landslides the pore water pressure accumulates or not. It's difficult to measure the permeability in the field, for sure.
Well, I said it's clear, and thank you. Do we have any more questions from the audience? If not, well, we can still have the questions towards the end, but if not, we really want to thank Professor Núria Pinyol with a round of applause from everyone. And I represent everyone here. And we move on to the next speaker, who is Professor Gianvito Scaringi from Charles University. He's my supervisor, by the way, for the people who don't know. And then he's, from Charles University, that's what I said. And he's a leading expert. I have a small introduction prepared for him. The leading expert in landslide dynamics, shear zone processes, residual friction behavior, and thermomechanical controls on the slope failure. Also chemomechanical, if I missed this one. This work has particularly been influential in revealing how temperature, shear rates, chemomechanics, and coupled physical processes affect residual shear strength and govern the landslide initiation, acceleration, and long run up. Okay, so let's put our hands together for Dr. Scaringi.
Thank you, Om. Good morning, good day, everyone. You can see from the Om's speech that he did not get his PhD yet, no? So it's very, very kind with me, no? Praising and said, joking. No, so yeah. And I want to thank you also, Núria Pinyol, for the very insightful presentation. We have indeed some differences in the results we obtain, and it's really it's not the first time we compare them, and it's very interesting now to understand and hear from each other's perspective. My presentation is more focused on the experiments, a little bit less about the modeling, and I will take also a little bit of a historical perspective on the issue, on the problem of thermal effects on soil mechanical properties in general. But let me start with my personal motivation to study this problem. As a PhD student, and then a young postdoc, I've dealt with landslides, with the study of landslides, and in particular with slow-moving landslides in clay formation. And the typical, the most common observation for at least non-seismic landslide that you can make is that these active landslides that are periodically accelerating typically do so after a wet period, or monsoon, or intense rainfall, or prolonged rainfall period, or snow melting. And the mechanism is what we all learn in class, it is a hydromechanical coupling. No, there is an increase in moisture or an increase in pore water pressure or decrease in suction, whatever. So there is a hydraulic condition that changes. You get decreased effective stress, and because of that, also the available shear resistance is decreasing, and because of that, you get remobilization, acceleration, and so on. But this cannot explain all landslides. Now, some landslide reactivation they don't follow this pattern, and in particular, what inspired my research was a study by Shibasaki and co-authors, co-workers at DPRI Kyoto, an about 10 years old study that took observational data from a group of landslides in Japan that were moving in quite a counterintuitive way. So then, and let's look at that. Let's look at the graph. What this graph says. So here you have in red. I don't know if you can see my pointer. Maybe no, but try to make it more evident here. So you have cumulative displacement. And you can see here there are some phases in which you have an acceleration of the landslide, and then it stops again, it slows down again. And then in the next year there is an acceleration and so on. And these accelerations are happening at the end of the year. You see September, October, November, December. And then they stop. Here you have the rate, the daily displacement, and they're not small. Here you have daily displacements also in the order of meters. So it's a landslide that really, really accelerates, moves some meters in autumn, and then stops again. But then if you look at the precipitation, you see, the summer is rather drier. Then the landslide starts before actually a wet period begins. And the wet, the moist, let's say, times are actually at the end of autumn. It's the winter here when you have more precipitation. And winter is actually snow, means snowfall. Quite a lot of snowfall, because you get up to 3 meters of snow cover in this area. It's quite a cold area, mountain area. But this precipitation, and here is the cumulative, is not changing pore water pressures in the ground. So this mechanism doesn't work. Pore water pressure remains more or less constant. It's a water saturated material. Probably the pressures are already high, and they don't change during the year. But you still have acceleration, deceleration pattern. And if you look instead at the patterns of temperature, you can actually see that temperature is increasing throughout the summer, end of summer. Then temperature starts to decrease in the autumn till it reaches zero, even close to the surface. Actually, the cover is freezing, even, but the landslide shear zone is deeper. So what happens? You have a reduction in temperature, which matches this acceleration of the landslide. So the authors make an hypothesis that this is a thermal effect in this slow-moving landslide, in the acceleration of this slow-moving landslide. And to me, it was really, really fascinating topic that prompted me to study a little bit more coupled processes in soil, so thermo, hydromechanical, chemomechanical, like Tom said, of course. Then the authors wanted to investigate. They had quite a good apparatus. It's the Sasa machine. Big ring shear. Also, we control pore water pressure, actually, which didn't use in the specific experiments. But what they did is that, let's look at how the residual shear strength is changing with the temperature. They find actually something a little bit different from what Núria showed you, because in their case, the effect of temperature is consistent, concordant, my student tell me to say, with the temperature. Temperature increases, the shear strength is increasing. This is a material, as you can see, this is not the landslide material, actually. It's one type of bentonite, which from the friction angle, it is really some very pure smectite because of really very low values and probably very smooth surface. But what is interesting here is that they observe an increase in strength with an increase in temperature and vice versa, weakening upon cooling. So the black points here, it's room temperature. At lower temperature, there is somehow 0.3 degrees, which is actually quite a bit. It's 10% less strength, which can explain when the landslide is moving, actually. The authors took this to a next level. I think actually what we are trying to reproduce, we are reproducing these results, but their their data set is already quite rich and quite interesting. So they figured that it is the smectite fraction in the soil, in clay soil, not the kaolinite, not the but the percentage of smectite that can be somehow correlated with the thermal effect. They do this also with the plasticity, and it still works. And as you can see now, the axes are the opposite. They were interested in weakening by cooling. So the points go down here because they represent weakening by cooling, and instead the white points are weakening by heating. But the effect is this one. No? Cooling means weakening, heating means strengthening. They verified in both directions. The more smectite you add, the more is this thermal effect. Now, this is a normalized measure, and you should read it like how many percent of residual shear strength change, or actually this is friction coefficient, but more or less we are there. Friction coefficient or friction angle, there is quite a linearity at low levels. So this -1 means 1% change in friction angle per 1 degree of heating or cooling. No, -1 here is -1% of friction angle per 1 degree of cooling. In this case, 1%. If you look at Núria's results, we are in this order of magnitude, just with the other sign, actually, no? Because Núria, you showed some 10%, 20% change under 50 degrees change of temperature, or 40 or 30 degrees. So it's 0.2, 0.3 value. But Núria sees a discordant effect. The authors here already attempt an explanation of this, because then our result also show this, no? So I try to understand, we do very similar procedures, so we obtain different results. It must have to do with the rate of shearing. Even though 0.4 millimeters per minute is a rather low rate, it's actually quite fast in terms of a strain rate for morillonites compared to possible lower rates, few microns per minute. So all these results by Shibasaki, all these black dots, actually dots and diamonds and triangles, are experiments at lower rate than Núria. So 0.01, 0.00 something of microns per minute, a few microns per minute, while look at this data here, and also this cross, this black and white cross. It looks like a black and white British flag, and you have an opposite effect. This is an experiment conducted on morillonite, sheared faster, no, at 0.5, 1 millimeters per minute. So there aren't too many experimental results, but it's quite clear that if you accelerate the shearing, if you do a faster shearing, you can actually make the thermal effect disappear. It seems that the thermal effect is very, very sensitive to the rate of shearing. So this is a variable in the laboratory that we need to consider, and also we need to consider how we extend our results to the field. Like what is the upscaling variable? Is the displacement rate on a surface? Is the strain rate within a shear band? So it's quite important then, because it can change how we model. What I want to add to this is that so while Shibasaki's results are probably the first that really investigate the residual shear strength, there is other literature that investigates other parameters of the soil behavior and how the temperature is influencing them. So you can see also in recent literature for energy geostructure or for nuclear waste repositories that there is an interest in understanding thermohydromechanical coupling with respect to compression behavior, with respect to hydraulic conductivity, with respect to development of swelling pressure. This is done both in saturated material, in compacted bed. So there is now quite a rich literature. And then the question is, well, the problem is then solved. Now we know behaviors, we have a rich experimental data sets. What for we do the research? No? So, well, the problem is not solved my opinion, because, well, we are still, like engineers, still work with classical soil mechanics, in which, in general, temperature is not considered, no? Especially in slope stability, except Núria's work, few more works on fast landslides, or work that consider freezing and thawing, so in more extreme condition, then yes, there is control of temperature. Otherwise, everything is done at room temperature in the laboratory. Actually, there is really no control. Like I say, oh, there is air conditioning in the room. It's more or less 20-25 degrees. But in some laboratories, temperature can also oscillate. And instead, in the field, the soil is always at different temperature, certainly not 20 degrees. In our climates here in the Czech Republic, we have like the underground stays at 7 degrees, 10 degrees of temperature, especially after like some meters of depth. Temperature is more or less constant. It doesn't change much. In colder climates, you have 3-4 degrees. In tropical, of course, soil, the ground is warmer, but it's different from the lab. Generally, it's different from the lab. And one first thing that I notice is that we don't account in our like classic soil mechanics for the temperature difference between lab and field, which can actually alter like all possible soil mechanical properties. By a little, by a lot, I don't know, but we need to quantify. And the problem is that actually in overall, anyway, the effect of temperature is relatively less studied, that we can get inconclusive results because we don't have standardized protocols now to do things. So depending on methodologies, apparatuses, testing, condition, over consolidation, so we can get different results. And so the thermal effect did not systematically go into norms, into handbooks. And also, there is another problem. Now, while rainfall-induced landslides or earthquake-induced landslides are something really self-evident, no? There is earthquake, there are thousands of landslides. It's still not so evident that you see, oh, there is global warming or there is a heat wave, and you have more landslide because it's hidden, no? It's coupled, it's complex. There are many other variables. And so temperature-dependent phenomena, you see them only in some extreme cases. Rapid snow melting at Svalbard or very fast mega landslide where you really see, yes, there is frictional heating, thermal pressurization, and so on. But this doesn't mean that the effects don't exist in all other landslides. No, it's simply they can be hidden, they can be coupled, and maybe simply they have not been studied enough. And in general, there are less models, there are fewer models compared to general soil mechanical approaches that account for temperature in soil mechanics. And MPM with thermohydromechanical coupling by Núria and others is one of the not so many examples of approaches. So Núria is pioneering, no, this field. It's not well established in this sense. So there are experiments, there are experiences, but not too many. And if you look, I like to look at history also. People arguing, for the importance of coupled processes or the importance of coupled of thermal effects were not many, but there are some like very notable examples. And one of the pioneers of coupled phenomena, coupled conduction phenomena, and so on, certainly was Professor Jim Mitchell, who already in the 60s wrote a collection, a report for the US Highway Research Board on temperature effects on the engineering properties and behavior of soil. This is a beautiful collection. It's a technical report with 14 papers published in the 69 commissioned by the Highway Research Board. The problem was they are building interstate highways in the US, in California. He was in Berkeley, Arizona, Nevada, great thermal excursions. These embankments get damaged. The Highway Research Board asked Professor Mitchell, is temperature a problem in the road embankments, and how can we study? So he made quite a nice and comprehensive collection, and he writes in the introduction that make possible a greatly improved understanding of the importance of thermal influences in soil mechanics, and then also in some application he wanted to explore also thermal treatment of soil. Little parenthesis, 68, 69 is the years where the NASA was bringing astronauts to the moon, and it was really a time of pioneer, and Professor Mitchell was also involved as a consultant by NASA, not for thermal processes, but to understand the possibility of landing on the moon and sampling lunar regoliths. So they asked him, as a geotechnical engineer, for opinion and some information on how to make the landing safe. So he actually played a role also in the Apollo landings. And in the same years, he was working for the Highway Research Board to understand thermal effects. A problem, what happened this year, that this study was really, really like pioneeristic, but it got more or less forgotten. If you see, it's not really cited much in the literature. It's kind of, it was considered a little bit of a niche problem, and it did not go break into the mainstream. But still, this collection by Jim Mitchell contains some very interesting pearls that also relate to the strength, thermal effects on the strength behavior of clay. So, for example, this graph shows the change in undrained strength of kaolinite with temperature. This, what we see here is a heating from more or less 24 to 66 degrees, and you can see the change in moisture content, so in porosity also, and strength with temperature for kaolinite. He argues, the author also argued that in general, compressive strength decreases with temperature, actually, but it relates to kaolinite, not to morillonite. And this other one, Noble and Emerald, in this collection is really, really beautiful. It's so systematic because this is the effect of consolidation temperature and shearing temperature on the peak strength of an alluvial clay. It's so nice because it tells you, look, if you consolidate at a high temperature, you get basically a better compaction, better engrainment, lower porosity, and then when you shear it, the peak strength is higher. But look, it also depends on the temperature at which you are shearing. If you shear a cold clay, it's more brittle and gives you a higher strength. If you shear a warmer clay, it's already softened. It loses this pre-consolidation effect of the high temperature compaction. This had practical implication in the construction of road embankments, actually. They were telling basically when you build the embankment and you compact it, do it in the summer, so it's better compact. And then here is how it can fail, the peak, if it's in summer or in winter, because the embankment can get also very hot under the asphalt. And these are quite nice, preliminary results after that, there was not really too much research about it, and it's a little bit of a pity. So now, back from the history, the 68, 69, to our research, I just want to show you what we did instead, to try to confirm and validate, the findings from the literature. We are in the Czech Republic investigating a number of slow-moving landslides. These are just 3 examples in one marine clay formation, the Březno formation, where you have materials that have medium activity. They have like a 70% liquid limit, 40 plasticity, 30 to 40 clay, 50 also clay fraction. Sometimes liquid limits also are higher. Friction angles around 10 degrees, 8 to 10 degrees, residual friction angles. And they are moving, these millimeters per year with some reactivation like fast phases in the past, over slopes that are quite gentle. This is not uncommon. It happens in the Czech Republic. It happens a lot in Italy on the Apennines. We have many slow-moving landslides on these clay slopes. What we did to test, well, here we did not have evidence in the field like Shibasaki had it. We don't have yet enough monitoring information to say whether this landslide is actually physically moving with the temperature changing. But we want to know in advance, before data come to us from inclinometer and so on, whether there can be a potential effect. We developed a very similar apparatus to that in Barcelona. It's a Bromide apparatus with control of temperature with an external water bath, thermometers that monitor the temperature in the water, and a system, a protocol to increase or decrease the temperature and observe the shear strength. This is work developed by Marco Locke first, and then by Dakal, our host today. So everything about it. I will just show you now a little bit of what we did. In general, we went with temperatures higher than room temperature. It was easier for us, but we also did some experiments at lower temperature, like 7 to 10 degrees Celsius, and we evaluate thermal sensitivity in our material on this order of magnitude, not 0.2% per degrees, but positive in the sense that we observe a strengthening upon heating or weakening upon cooling, which is consistent with the observations of Shibasaki. Interestingly, this effect persist in a range of shear rates. So we go here at 18 microns per minute. This is 0.1 millimeters per minute, 0.2. Although when we get into faster rates, so 1 millimeters per minute and up, the effects start to fade away, start to disappear. But like we discussed before, it gets complicated. Material starts to be extruded outside the pore water pressure. We don't know what is happening about pore water pressure because we are not measuring them, at least not yet. We are trying to develop something to measure, to try to measure pore water pressure. And so we don't really trust the results at 1 millimeter per minute or above, and we consider instead the results that we obtain at very low rate. As you can see also, thermal effects are really not evident. There is too much noise at low rates of at low confining stresses, but when you go at 150 kilopascal, you start to see some evidence. We try to explore two protocols. This is a protocol in which the experiments are completely distinct. So we do one sample and we test it at room temperature. Another sample, we test it at elevated temperature throughout the experiment. So like if the sample exists at 70 degrees only. Of course, it makes more issues because you need to prove that it's repeatable. You need to make many experiments at each temperature and do some stochastic analysis, statistical analysis to be sure. So these are just two trials. And you see that there is some thermal effect, and it's in the order actually here of 0.1% per degree, not too big. Instead, this is like the more, let's say, classic approach that Shibasaki used and Núria used. We also use. Now you shear at room temperature, then you increase the temperature or decrease the temperature, and then back to the previous value. And from here, you interpret the change in strength with the temperature and try to produce a correlation. In this case here, we do different steps at 50, so 70, 50, 40, 30, 20 degrees to take more points, waiting anyway. This is very low rate of shearing, so these are many hours. This is 1 day of testing, another day of testing, so it's quite a long experiment at 18 microns per minute with this, 20... I don't know, 20 millimeters, 15, 40 millimeters, I don't remember. So some tens of millimeters per day. So the experiment lasted for long, and I quite trust that there are no residual excess pore water pressure. We get into a drain behavior, and we can get some linear correlation between friction angle and temperature, which gives us, in this case, it's about 0.3. We don't know what methods is better actually, so for now we say that our landslide soil has a sensitivity of more or less 0.2% per degrees when it is slow sheared. I want to show you some older results that we got on more pure clays rather than the landslide material, because landslide material is anyway a mixture. We know that there is some smectite, but there is also some kaolinite, some illite. It's really like a mess. No, it's quite heterogeneous also. But if you work with pure bentonite or kaolin, you can see a little bit better the results. So I'm showing you some older results by Marco Locke, and these are the first results, the first experiments that we carried out, 3-4 years ago, where he was testing. This is a calcium bentonite, not the most active, but quite active. And again, when you shear it very slow, you see that you increase the temperature, and we still had some problem controlling the temperature, as you can see here. Increase the temperature to 50 degrees, you have some peak of strength, then there is some decay, probably some dissipation of pore water pressure, and it seems to tend towards that steady state. Then the machine was not refined enough here. We had to stop it after a few hours. Now there is a better system to refill the water and so on. But you still see here, there is some peak, some decrease, and some steady state probably at the end. But the effect here is concordant: higher temperature, higher strength. If you look at same experiments on a non-smectite, on a kaolin, you don't see this change in strength. Here there is some problem in the experiment. Here you even seem to notice some little decrease, no? Some opposite effect. You increase the temperature, maybe the strength is decreasing, but it's really negligible for like the precision that we can achieve. But what is interesting is that when Marco did the experiments at a higher shear rate, but not too high. So again, we settled for 0.5 millimeters per minute, which is consistent with Núria's experiment. Well, this concordant effect completely disappear and some discordant effect starts to emerge, although we already, the strength here already started not to be so clear because probably there is not perfect alignment of the loading cap, etc. So you already have some difficulties trying to interpret the residual shear strength itself. But what is clear is that we don't see increase in strength with an increase in temperature. Possibly there is a decrease, although it's insignificant. Statistically here we cannot say much. But on the other hand, we do see and this is even a bit highest rate for the kaolin, but kaolin has much higher permeability, so probably still okay. That on the other hand, a fast sheared kaolin displays a concordant effect with the temperature. So there is, you see, there is really like a cross here, like a swapping of behaviors. Now, the bentonite, slow shearing the bentonite gives a concordant effect, fast shearing it gives a discordant effect, and kaolin has the opposite effect. So there is quite some mineralogical control that I actually cannot explain because I did not perform like some micromechanical or mineralogical investigation. But what I can say is that more or less our results are consistent with these available data sets, both for slow shearing and for faster shearing, although Shibasaki did not test kaolin under like a high rate. Probably it would give some results down here and we are missing. So it would be interesting to improve this visualization with an extra axis or with two charts showing the thermal effects as a function also of the shearing rate and as a function of mineralogy. I want to add also some more recent experiments that are actually recently published experiments by Om Dakal, where we moved back from pure clays to natural soils, choosing, this is soil from Nepal, which is different from our landslide soil that has smectite. This soil has no smectite, has mainly quartz sands and silt, and some clay that is probably more like kaolin. It's less active. It's certainly a less active clay, and it's quite interesting that in the experiments, these experiments by Ohm show instead a discordant effect. So the strength is decreasing with temperature, and the amount of decrease is proportional to the clay fraction. So if you have no clay, no thermal effect. If you add clay, you have a negative effect. And these experiments were done at 0.1 millimeters per minute. But we have low amount of clay fractions here, noise, some scatter. But what is important to me, to make an argument later, is that we can see the effects. This is the white points are like the white markers signal no effects or statistically insignificant effect. We analyze the data statistically, and the markers that are colored in red gives us statistically significant differences in strength according to the different temperature, 50 versus room temperature. So if we have at least some clay fraction, if we test in a bromide under 100 or better 150 kilopascal of normal stress, we are able to statistically say that there is a difference in strength between a sample that is sheared at room temperature and a sample that is sheared at an elevated temperature, independently of the amount. So the amount here is very small. We are looking at 0 point something degrees in friction angle, but the effect is measurable. And to me, this is quite important. Now, back to the field, because I'm talking for too long. I want to add that in the field we put thermometers in the ground, at depths down to shear zone. This is one example for the first month of testing last year. We have more data now, so we can actually see how the ground is getting warmer and cooler during the season. You can also see the delay in heat transfer in the ground. So we are just confirming what is expected, of course. We can, using thermometers in the ground, estimate thermal properties of the ground. And with this information, we can develop some simple thermomechanical model, no? And just a model for the shear zone to understand how the strength is changing and then quantify changes in friction angle. This was more or less mostly a parametric study that I'm showing here, based on a geometry that is similar to that of the landslide in the field. Now, 8 degrees, 7.6 degrees of slope. We use depths, which we parameterize. We try with 3 meters, 5 meters, 7 meters shear zone depths, which represent various landslides in the area, no, some shallower, some deeper. We have like a half a meter shear zone, which is what seems to be from the course, from the coring. And we assign properties based on our experimental investigation, so odometer, triaxial, and ring shear. And what is important, we apply a more Coulomb criterion for the failure, no, of this landslide with a temperature-dependent friction angle, linearly dependent, which is confirmed by experiments. And we try with our field data of sensitivity, and we try with the extremes found in the literature relative to very, very slow shearing. Anyway, so shearing done at the minimum possible rate allowed by the machine. And we do an extra step. We try to apply temperature data series, which we take from meteo stations that have like decades of recording at the site. And we add also some warming scenarios for projecting future heating. We build some thermal profiles in the ground. So we reproduce. The central one is what is the actual profile, the current modern profile. The blue one would be like the cooler past, and the red is the warmer future based on some warming scenario. This is quite a, I think, like a bad scenario where the temperature at the surface is increasing by 3, 4, 5 degrees over a century, which is possible because we already, in the Czech Republic, we already had 2 degrees of warming at national level, and we expect more. It's quite higher than average. And here you can see the seasonal oscillation. Also this plot, the envelope shows seasonal oscillations. And if you move from one of these flowers to the other, you get the heating after several years. We can compute using these envelopes. This one is relative to present situation, calibrated to have a factor of safety 1, so back analyzed so that you have 1 because landslide is active. And we can see what we expect in terms of changes in friction in factor of safety in this simplified landslide geometry with the seasons, and depending on the depth of a existing shear zone. So at a depth of 5 meters, for example, we get for a soil that has thermal sensitivity a change in factor of safety in the order of 2, 3, 4%, which adds to hydraulic effects. I don't quantify hydraulic effects here. I'm just saying, look, considering temperature gives you some seasonal oscillation of the factor of safety. And then if you move from the past to the present and to the future, let me help you interpret this graph, you are also changing the value, the range in which the factor of safety is oscillating because of temperature. So let's imagine for a shallow failure at 3 meters in residual condition, because of seasonal temperature oscillation for a material that is very sensitive to temperature, so a pure monorilonite, so a very active clay in the field, you would get winter factors of safety of 0.85, hypothetically, and summer 1.05. So this would be a landslide that goes below 1 seasonally. It stops, it reactivates by cooling, it stops again in summer, for example, here. Present times, also you have oscillations around 1. Again, this is calibrated so that we can show this. It's not the real condition of our landslide, but again, you have a longer period of stability during the year and some period of instability. Hypothetically, with warming, with higher temperature in the future, you might get to a situation in which, no matter the season, the factor of safety stays above 1. So what I'm saying is that it might be possible, no, in certain conditions, in certain soils, that we will detect landslides that are seasonally active now, and they can become dormant just because the ground got warmer by several degrees. Of course, I use this picture because it shows nice results, because the material that I use here is very, very active. No? This 1.8% per degree, it's like really a pure monorillonite of strengthening. If I go on more like normal soil, 0.2, 0.3, 0.5% per degree of thermal sensitivity, the effect is smaller. So take for, or if I go to deeper failures, no? So here is the oscillation at 7 meters. At 5, at 3 meters, the oscillation is 1% in friction angle, and the decrease over a century also is in the order of 1% or something. Maybe negligible, no? Probably a second order effect compared to hydraulic triggers, that for sure. No? Maybe in the future there will be different pattern of precipitation, or more intense, more dry in some area, and that will be certainly the dominant effect. No? Here, 1%, it's small. But is it negligible for the kinematics of a landslide? Well, I say no. No, in certain conditions, 1% and even less can actually do a lot. Now, if you have read, there was one study published in Nature Geoscience in 2009 by Bill Schultz and Gonghui Wang from the PRI, Schultz from USGS, that actually correlated a rate of a landslide, an active clay landslide, with atmospheric pressure. Even atmospheric pressure is a small, very small forcing on the landslide. It's atmospheric tide, basically. It can change pressures of air in the pores, and if the mechanism does not dissipate, because it changes quite fast when there are storms and stuff, actually it can slightly pressurize or depressurize the ground. But they did some very nice and fancy calculations on that, but what they got in the end was the change in atmospheric pressure would change the safety factor of that landslide, which is an active landslide, by 0.1%. And even this 0.1% oscillation can be correlated, if you are refining now, to phases of acceleration and deceleration. These are day-night acceleration and deceleration of the landslide, which is amazing. No? So we actually are able to observe 1%, 0.1% effects. Now, the effect of a 0.1% change of some quantity, of some boundary condition, can actually have a measurable effect on landslide. So I argue that even what we find, there is a difference in 1%, we should not just say, no, it doesn't matter. It might matter under certain conditions, and it's worth exploring it. One more thing I want to say about our study is that we did like decoupled numerical analysis. So we say, okay, what changes with changes in temperature? What is the change in safety factor with the depth of groundwater table, for example? So we introduce a hydrological forcing, and then we combine them, and you can see here the effect. So I don't have time to explain, but imagine that the slope is dry and there is no pore water pressure, and we do the analysis in total stresses. Then we can do the analysis with water, we can do the analysis with temperature, and then we do a thermo-hydromechanical analysis where the two things are combined. There is no like full coupling, but we are just considering these two effects. And what we notice is that the sum of the effect of the coupling in a model has a larger effect than the sum of the individual effect. And this is important, because if you say, water matters for 10% of friction angle of safety factor, and temperature matters for another 10%, the total effect is not 20, it's 30, it's 35. And this tells us, look, we need to perform more systematically coupled analysis. Oh, this is simple, it doesn't contain many couplings, but you can do with more and more. And to conclude, it's already, I see here, and you need to finish. to conclude, what I want to say, I take it from far, I know, because I like the historical perspective. But think of this. Soil mechanics started as like a science, even not a standalone science, in the 18th century, no? Coulomb. Then modern soil mechanics, and this is, and this is Cartezaghi, a giant, so I draw it very big in the slide, a giant of soil mechanics, and we move to hydromechanics systematically in the 20th century. Thermal problems are typically deemed negligible, but now, contemporary soil mechanics, 21st century, we have more knowledge, we have more technology, and I think we need to reconsider some of the simplifications that we make in our classic thinking in our discipline. We do have challenges, we do have uncertainties, of course, because more we investigate, more we find issues. But in general, we are able to better constrain certain processes, and in general, we do have fewer uncertainties in our understanding. And if the uncertainties are less, then some effects that we say they are in the noise, they are negligible, they are not anymore negligible. So we need to acknowledge the complexity of soil, but at the same time, we need to embrace this complexity and work and not be afraid to work with coupled processes and coupled models. And that's it for me. Thank you very much for your attention up to this point, and I'm available for questions.
Thank you, Vito, for putting up a nice story and all the effort to explain this topic. Yeah, so I already see a few questions. I asked all of the audience to have more questions, and let us close this session with a thorough discussion. Yeah, so you could either write your questions on the chat or just go ahead and unmute and ask it. So I would first start with a question from Chitis. It says, is this relevant for soils or only for soils only or rocks? Sorry.
Well, actually, thermal processes, the temperature affects rock mechanics a lot, but the processes are a bit different. In rocks, you have much lower porosities in general, but there is an effect on the thermal expansion of the material, opening and closing of cracks, heat diffusion in the cracks. So yes, it does matter in rock mechanics, but we cannot study it in the same way. There are distinct processes. And then, for example, in fast shearing, it's also very beautiful. Now you can carry like a rotary shear at very high speed in rocks, and you obtain all other sort of processes, of phenomena. Now, if you have saturated clay and you are shearing it fast, you pressurize the pore water, you heat the pore water, water is expanding and so on. But if you are shearing a rock against another rock surface very, very fast, you are heating the rock, and sometimes you might even melt the rock. So you can get mineral melting and recrystallization. You get pulverization of the rock that is completely crushed. So there are other phenomena, and there is quite some literature about it, and it's very, very fascinating.
The follow-up question is, what precautions are to be taken for slope, especially for hydropower projects and damp slopes? Any examples?
Wow, that's quite interesting. I haven't thought about it. But yeah, I know that, for example, in China is a big problem of the landslide happening on the sides of hydropower basins. And some slopes that were like up on the slope, and now they are submerged basically by the basin. I don't know actually, because if the slope reaches a water basin, probably the water in the basin kind of regulates the temperature of the adjacent slope and reduces the thermal excursion, which might be good actually from the point of view of thermal effects, but I think it has to be studied more in detail. I don't know whether some specific precaution has to be used, but what I would advise, where possible anyway, is that if in the laboratory the experiments can be conducted at a temperature that is more similar to the temperature of the field, I think we could get some additional accuracy in our evaluation. But again, also it's a bit questionable, because if the parameter is not too sensitive to temperature, and so if you are changing the friction by 0.1%, but the machine itself gives you an uncertainty of 5%, then I would say it doesn't matter. You can do the experiments at 20 degrees or at 30 degrees or at 10, you will not see the difference. But if you are doing some high precision evaluations, then temperature should be considered. And it's not just for hydropower, in general in soil mechanics, in my opinion.
Yeah, so before I read out the follow-up question, if there are more questions to Professor Pinyol, you can also ask as he is still in line. But I would first read the question in the chat. Do you plan to include the shadowing effect of the vegetation, of the penetration of heat in the soil? From site measurements, I have seen it may play.
I agree, Vito. I agree with you. Like if you have like quite some vegetation and the sun does not hit directly the surface of the ground, I'm quite sure that the penetration of the heat would be altered in a non-negligible way. I agree. The thermometers, the boreholes that we installed in the site are in basically bare areas. So the sun hits directly, and moreover, it's south-facing slope. So probably the effects are amplified on those slopes. But if we have the funding in the future projects to install boreholes and put thermometers in a forest, for example, or in when there is denser vegetation, I'm quite curious to see also there how the heat propagation, the temperature, the shear zone depth changes, and if there is any measurable later effect. So I agree. Yes, I would like to do it.
Yeah, thank you, Vito, for the question. I see a hand raised from Núria. Please go ahead.
Thank you, Vito, for your presentation. Really interesting. I know your work, but I always learn it a lot. How do you explain the effect of the normal stress? Because when we try to find a theoretical framework to explain the effect of the temperature, we went to try to go to micromechanisms controlling the strength and thermally activated, following Arrhenius relationship. And usually this expression, these theoretical equations, the strength is always as a factor of the effect of the temperature, in the sense that if the stress is larger, probably the effect is larger or slower, but in a proportional
I agree. No, I did not investigate this in on micro. I didn't study enough. I need to study more that. What I can say that to me, I think that shearing under a certain normal stress helps the formation of a smooth shear surface, and so that we can see the effect. So I think that at 100 kilopascal, at 150 kilopascal in the bromide, I can trust more that we are in residual condition, first of all. I don't really trust what I see at 50 kilopascal in our machine, because in my opinion, that residual is not so clean. In fact, we get some higher friction angles. And so if you don't get a nice laminar shearing at room temperature, and when you change the temperature, I don't know really what happens. So if I have a wavy surface, if the shearing is a bit turbulent because of not enough confinement, I cannot really explain. And in fact, we don't see much at those levels. And then there is simply like a matter of uncertainties of the machine, Like our load cells are calibrated, and there is like a certificate which tells us, it's plus minus, say, 1 Newton, And that 1 Newton of shear force matters a lot when it's under 50 kilopascal. And it matters much less at 150, so it makes our evaluations statistically insignificant also, independing of what we see also. But we cannot really make like a conclusion if the normal stress is too small. But then from the physical, please.
But the samples were had the same overconsolidation or normally consolidated, because then the normal strength changes the structure of the compactity of the sample. But for sure that it is very different, because the structure of the material is completely different. So you load it and then unload it, and then you apply it.
We did both ways, but I think the experiments on this Czech clay, correct me if I'm wrong, were done without over-consolidation. I think now you do it without. We are trying to do it without. So you progressively load, and you don't like load and then unload. But on the bentonite, I'm sure we did the opposite. Over-consolidating the bentonite and then shearing at 150, then shearing at 100, then shearing at 50. So we were going backwards in stress. So the material, the non-sheared part of the material was over-consolidated, because then the thin layer at the top that we are shearing, well, that is not over-consolidated anyway once it's sheared. It starts as over-consolidated. Yeah.
Because if we are coming back to the discussion that before we have, if we have a effect of couplings,
yes,
in the sense, if we don't ensure that the structure is the same,
yeah,
and
agreed.
then we cannot ensure that.
I agree. I have more results that I did not show, because our postdoc in the past year also did more experiments looking at the stress history, looking at the actual water content of the material. So we are still putting those together. So I didn't show it because I didn't have still a full interpretation. But yes, in the end, yes, it's quite, to me, it's a little bit surprising, because I learned that residual shear strength does not have any history effect, because the material is a post-failure material. There is no like remaining structure from the before, but still in our machine we do see something, because it has to do with the behavior of the material which is underneath, which works as a different boundary condition. Basically, if you think that you have a thin layer that is being sheared, but then the bottom of the sample is not really sheared, and it remains over-consolidated. It remains with different thermal conductivity, different hydraulic conductivity compared to a normally consolidated material. So it still plays an effect, because then the boundary, even if the residual shear strength has no history in itself, the boundary condition is different. And this might mess with our results and complicate them. So it's very fascinating.
Thanks.
Yeah, thank you. Let's follow up with one more question from the chat. Yonten says, if the slope is covered with vegetation, do you think the effect of temperature to slope stability will be impactful?
And that connects with Vito's question as well. I don't have enough data to see to give an answer, but in principle, yes. Vegetation cover acts as a filter between the ground and the atmosphere. So it modifies what the ground feels from the surface. It certainly reduces daily temperature oscillation, probably the seasonal one as well. It changes how moisture is transferred into the ground. But I think that in the long run, maybe it does not have an effect for the long term. I mean that in consideration of global warming, if you give the ground 100 years to warm up, no matter the vegetation, so it's simply like the thermal conductivity will be lower overall, let's say, but then even with vegetation, the ground will get warmer overall, from the side, from the top, or slower. So I think that we need to then make a distinction between short-term effects, seasonal, daily seasonal, and the long-term effect of the changing temperature. And it's quite interesting. We should do more research about it.
Thank you. There is one more follow-up question from Chiti. It says, should temperature-dependent reduction residual shear strength be incorporated into slope stability design criteria for Himalayan hydropower projects under climate change conditions?
Well, it's not up to me to decide whether this get into design criteria. It's early, let's say, before we tell engineers you need to do this way. I mean, I say that I advocate for this, but I argue from a scientific point of view. Then the results need to become like solid, verifiable, repeatable. We need protocols for evaluation, a standardized system to tell the laboratory how do we measure thermal effect, or how do we measure like to answer also to Vito, the effect of vegetation on the condition. Now, once we have a solid answer, which requires decades of research typically, then we can tell engineers, okay, incorporate a 0.1 thermal coefficient so that you stay on the safe side. So yeah, I mean, in the long run, again, I would like to have consideration, suggestion, advices about temperature incorporated into norms, into design criteria, but it's early. It's early, of course.
So, is there any more burning questions? Last chance. Yeah, if not, I would. Yeah, this was quite a long session, I should say, and was very interactive. I enjoyed it the fullest. I think. I hope the rest of the audience also did. Thank you, Professor Núria Pinyol, Professor Gianvito Scaringi, for your presence, for your effort in putting up the work together, and for the insightful discussions. Yeah, and representing the whole audience, I would like to give a round of applause, and you can also see flying claps. So that would say it all. Yeah. So if there is no last comments, and then I have to check. Yes. So then I would like to close the session. Thank you very much for attending, everyone.
Thank you very much, Om, and thank you to the e-YEG for organizing this webinar. It's really nice.
Yeah, thank you for organizing these webinars and for sharing a lot of information in the web page. It's very interesting.
Thank you. So yeah, have a beautiful rest of the day or night, wherever in the globe you are from. I would just like to subtly also announce that this webinar is recorded, and I would put it later into our e-YEG YouTube platform, so that people who couldn't attend now because of the global timings can attend later and listen to it and follow. Yes. So thank you very much. Bye.
Thank you. Bye.
Bye, everyone.
Thank you very much for your time.